Alright, so we have another Atwood machine. This is from the 1987 Physics B exam. And so we have two blocks, M1 and M2. M1 is on a horizontal table. And we are told that it is rough. So this means that there is friction present. The string that attaches them passes over a massless, frictionless pulley. And the coefficient kinetic friction between M1 and the table is mu k, and the table is less than the coefficient of the static friction, which makes sense. They don't really need to tell us that. So let's look at the forces on M1. So we have the normal force, we have M1G. It should be equal length here, and we have the tension. And to the left, we have the friction force. And right now, we do not know enough information of which direction it's going to be moving in. So if they're about the same length, right now that is okay. Well, from the information given to us from part B, it basically tells us that it is initially at rest. So at the beginning of the question actually did not tell us that, but now we know. Okay, so we're in static equilibrium right now for part B. Okay. So what that should be is that the friction should be static friction. So from the previous question, it should be static friction. So it should be Fs, not Fk. But anyway, we know that normal force minus M1G is equal to 0. So therefore, the normal force is equal to M1G. And in the x, T minus Fs is equal to 0. So therefore, T is equal to Fs. Okay. So what is the minimum value of the coefficient of friction that will prevent the blocks from moving? Okay. Well, there's a lot of things that we need to clean up, and everything that I've done here is only for block 1. Okay, if we look at the force on block 2, well, luckily it is just T minus M2G is equal to 0. So we get that T is equal to M2G. Wow, we have two equations for tension. Okay. Part B says that we can only use the variables M1 and M2. Okay, so we still have some algebra left to do here. So we know that T is equal to Fs, and it is also equal to M2G. Well, what is Fs equal to? It's equal to the coefficient of friction times the normal force. That's equal to M2G. What does the normal force equal? Normal force equals to M1G. Okay, so look. So, since gravity cancels out, we get mu s is equal to M2 over M1. And that's the answer to part B. Part C. We're looking for the acceleration. And we can only use these terms. M1, M2, mu k, so now it's sliding friction, and G. So how do our equations change? So for block 1, in the y. In the y, it's still in equilibrium. Okay. So still normal force minus m1g is equal to 0. So the normal force is still equal to m1g. We have that from earlier. And in the x, it's now tension minus the friction force. Okay. Now for block 2. We have tension minus m2g, and that's equal to minus m2a. Okay, it is minus because it is accelerating downwards. Okay, so I already distributed the negative sign from the a. Okay. So this is really similar to the Atwood machine derivation that you did for your lab. It doesn't really matter what we do, but we need to solve for t and substitute it in the other equation. Okay? Doesn't really matter which one. So I'm just going to use the one for block 2 because I have the most room there to write. That's honestly why. Doesn't matter. So if I add m2g on the other side, I'm going to get m2g minus m2a. Okay? Or m2g minus a. So if I input this over here, okay, then I get m2g minus a minus our friction force. Set that equal to m1a. Well, remember we can rewrite static friction as mu k times the normal force. And what is our normal force equal to? Normal force is equal to m1g. So m2 g minus a minus mu k m1g is equal to m1a. Now I actually shouldn't have cleaned up the m2 g minus a part, so I'm actually going to have to re-expand that. Poor foresight on my part, but it doesn't really matter. Pretty easy. Okay, so I need to get these two guys on the same side. Luckily, I can just add m2a. So we're going to get m1a plus m2a, and over here we have m2g minus mu k m1g. So a m1 plus m2. And now, if I want to, I can factor out g. m2 minus mu k m1. Okay, so acceleration is equal to g m2 minus mu k m1, and then now I can divide by m1 plus m2. And voila, that is our answer for number C. Now that we know the acceleration, we can solve for the tension. So going back, I said that tension was m2 times g by the times the quantity G minus A. So T is equal to M2 G minus A, and now I can just substitute our value of A, which is quite messy. So M2, and then, so I'm actually going to re-expand this out again. I just find it a little bit easier. And then for A, I get to plug in all of this. Alright, is there anything that I can really clean up? Slightly. Okay, so let's see what simplifying we can do here. So I tried redoing my algebra and I keep getting this answer. It's not wrong, I'm going to admit I can't simplify this that well. I mean, yeah, I could pull out G, but the solution says that it is M1 M2G over M1 plus M2 times 1 plus U. And I'm just having a hard time getting that. And I'll be real with you. But what I've done so far is right. I'm blanking right now on how to simplify that. So anyway, the concepts of this are still correct. And sorry about that, but I hope it helped.